All right, it's time to talk about topic 16.6, weak acids. Now, in the last topic, we got into strong acids, strong bases, and it's important that you can identify the strong acids. Every other compound that exhibits acidic behavior is considered weak, and that's because they would only partially ionize when they're in solution. So you'll have mostly the molecular form of that compound, and a very small portion of it would form the hydrogen ion. So reaction of these substances, you're going to see we have our molecule, the acid right here. It's important to get that A acts as a placeholder here. It's supposed to just represent any ion that would be used to pair up with hydrogen to make that acid. So we have our full form up here making hydronium. We'll generally focus more on this form of the reaction just because it's a little bit simpler. We leave out water because the water itself is not a significant participant here. It's the ions that matter. Now, remember, it is really important to note that this is a reversible reaction. It has an equilibrium. So, since it has an equilibrium, we can write out an expression for the equilibrium constant, which we've treated as Kc before. Since this comes up so frequently in a lot of compounds, we're going to change Kc into Ka. Now, we can express that Ka with the hydronium or with the hydrogen. I'm going to focus once again on the simpler of the two. We're just going to say Ka is the hydrogen ion concentration times the anion ion concentration divided by our molecular acid molarity. For a visual example of what's taking place, we can see right here, the strong acid is over on the left. You're going to notice that there are no combined anions. On the opposite end, you're going to see mostly combined molecules, and then you will have very few of those particles that separate off with hydrogen to make the hydronium ion. Here are some common weak acids that we would find in nature, along with a structural formula, the conjugate base of that acid, and the Ka value. And you're going to notice that many of these Ka values are going to range between 1 times 10 to the negative 2, negative 4, 5, 8, all the way up to 10 to the negative 10. It's very common that we have Ka values in this range. And you'll note that very small K values are always going to indicate that most of what you find is going to be on the left side of that reaction. The reactants are favored, is another way of saying that. Okay, so the reactants are favored. We have mostly molecules. We have very few ions, relatively speaking. Now, as a comparative point, please remember that K values always tell us the tendency of an acid to ionize. So, larger the Ka, the stronger the acid will be, right? So, there are several skills that we're going to have to build in this process. The first is how to calculate Ka using pH values. So, we're going to use our pH as a starting point. You're going to have to not only know the Ka expression, but you'll need to know the concentration of all the ions in solution in order to find a Ka value. Now, typically, instead of having a concentration directly, what we can measure is pH. As we indicated before, using a pH sensor that gets the passage of electrons through the solution, telling us how much hydrogen is present. So, our steps are going to be as follows. We first use the pH to determine the hydrogen ion concentration. The anion, remember that other ion we had talked about? It is usually going to be the same concentration as the hydrogen because they come together in a 1-to-1 ratio, that Ha breaking down into the hydrogen and into its anion form. So we can find hydrogen from pH as our first step and make the assumption that the anion is the same as the hydrogen. We will then write out the equation and the Ka expression. So here we have our equation that I've given. The Ka expression, remember, is going to be the hydrogen concentration multiplied by the anion all over the molecular acid What we'll do at that point is then substitute our known variables into our equation and solve for any unknowns. Okay? Now, it's a little bit challenging just to sort of visualize this here, but as we do some practice problems, this should hopefully make a lot more sense to you. The next concept here is percentage ionization. So another way to consider how much is being ionized is to put this in percentage form. So our percentage is going to be our concentration of the ionized hydrogen acid over the original concentration. I like to think of it instead as the hydrogen concentration at equilibrium divided by the molecular acid initially. So equilibrium hydrogen divided by the starting acid times 100 to get that into a percentage. So let's do an example on this one just to help sort of clarify your idea. If I have a 0.035 molar solution of nitrous acid, notice this is not strong, it's one of our weak acids, and we state that it contains 3.7 times 10 to the negative 2 molar hydrogen ion, we can find the percentage ionization using this data. Remember that the hydrogen at equilibrium is what's shown here, the 3.7 times 10 to the negative 3 molar. Our 0.035 molar is the original acid concentration in its molecule form. So take that number, divide it by 0.035, multiply then by 100, and you get 11%. Third skill that we need to form here is how to use a Ka value in order to calculate pH. So there's some specific information that's necessary in this form. If I have a Ka value to begin, and I know initial concentrations of our weak acid, well, we can use an icebox in order to help us understand how this comes together. So let's just say we want to know the pH of a 0.30 molar solution of acetic acid. Well, the 0.30 molar, let's remember, this is the concentration of our acid initially. Okay, so that's the starting value. pH is going to be the pH of the solution once it has come to an equilibrium. So it's pH at equilibrium. So here are the steps that we'll take. First thing that you want to do is make sure you know what the ionization equilibrium equation is going to be. We begin here with acetic acid, that is our CH3COOH, the combined molecular form. It will separate off, it'll ionize and take one of the hydrogen ions, and then we will have our CH3COO-, the acetate ion, is remaining. We're going to write in the Ka expression and plug in the known Ka value. So for AP chemistry, we will typically give you the Ka value in the problem. Here we're taking the number from table 16.2 above. And we find that our Ka, 1.8 times 10 to the negative 5, is a given, and that would have to be set equal to the Ka expression shown here. Now, the next stage is to consider using a Rice table. We're going to use our initial concentrations here. We remember that the molarity of acid given in the beginning was 0.30 molar. Well, as we begin the process, initially, we don't have any hydrogen, so that's a 0. And we also don't have any acetate ion that's been dissolved away from the original molecule. Our change can be expressed in terms of x, so 0.30 minus x. It's a 1-to-1 ratio for everything here, so we're going to gain x here and here for our hydrogen and our acetate ion. What that would leave us with is 0.30 minus x on the initial concentration coming to equilibrium. Then we have hydrogen with an x, and we have acetate as an x. So the final piece of this puzzle is to substitute these values in terms of x into our expression. So there's this x value, the other x value, but these are the same number, just see where I'm taking them from. And finally, we have the HA value. That's the combined molecular acid. So we have this equation in terms of x. So we're going to make an assumption here, and that assumption is that the initial concentration of our weak acid is very large compared to the change. What that means is this x is so small, we essentially treat it as though it's negligible. Now, we can disregard it. We're saying that that x is so small that it doesn't impact the overall concentration by a significant margin. And I can rewrite this as x squared over 0.30, the minus x has gone away, is equal to the 1.8 times 10 to the negative 5. At this point, we can do the math, solve, and work back through to find our pH as seen here. So take a second, make sure that these steps make sense to you, and then we're going to move on. Our validity is really important to know whether or not we can take this value. So if x is more than 5% of the initial concentration value, we should not assume that that x is small. And what we're going to have to do is go back and use the quadratic formula instead. Well, in this case, we've determined that 2.3 times 10 to the negative third is the amount ionized. That's the molarity of our hydrogen or our anion. We're going to use that value and compare it to the initial concentration of our acid. So 0.0023 divided by 0.3, multiply by 100 to make it a percentage, and we find this is only 0.077%. So we have less than 1%. It's definitely less than 5%. So it's a safe assumption for us to say the change in our initial concentration of our weak acid is negligible. So last idea here, give it some thought. If we have a 1 times 10 to the negative 8 molar solution of hydrochloric acid, and we know it is going to have a pH either less than 7, equal to 7, or greater than 7, well, let's just consider what is going on. 1 times 10 to the negative 8 molar. This is an incredibly small concentration of our hydrochloric acid. Well, if I know that 1.0 times 10 to the negative 7 molar is the hydrogen ion concentration when a compound is neutral, if I have any number that is less than this, such as 10 to the negative 8, that means that I have a greater concentration of hydroxide compared to the concentration of hydrogen. So that means my pH should be greater than 7 in that case.